Now, as I said that today, inshallah, we are going to study the chemical reactions, which means that we are going to study the rates of reactions, whether reactions are fast or slow, whether, or I mean, what are the conditions that we are going to use in order to increase the rate of any reaction? Because as you know, in industry, reactions should be a little bit fast so that we can get our products as we say as soon as possible. We can get our products in a small amount of time so that we can synthesize more and more of it. So to know the conditions at which we should work with in order to increase the rate of any reaction, then we have to study what are the rates first. How can we determine the rate of any reaction? Okay, so
Mhm.
to determine the rate of any reaction, we either measure the amount of reactant that is used up per unit time, or we measure the amount of product that is produced per unit time. We can study either way. Either we study what happens to a reactant with time. Of course, with time, any reactant, its concentration will decrease with time. So we study what happens every half minute or every a minute or 5 minutes, whatever. What happens to the concentration of this reactant? Or if we are going to study what happens to the concentration of the product that is going to be formed. Of course, for the product, it begins with zero because at the beginning of reaction, we don't have any product yet. But this concentration of product will increase with time. So we study what happens to this concentration with time. Okay, of course, we have many experimental methods to measure the rate of the reactions. We are going to take examples of some of them. So, for example, if I want to measure the rate of a reaction at which a gas is produced, one of the products is in the form of a gas. For example, if we measure the rate of a reaction such as magnesium metal reacting with hydrochloric acid to give magnesium chloride and hydrogen gas. So we see that here one of our products is a gas. So we are going to use this gas produced and measure its volume produced per unit time to take an idea about the rate of this reaction, to study the rate of such a reaction. So of course, any gas, when it is formed, it forms bubbles in the reaction mixture, and we can collect this gas either by two ways. As we have seen at chapter 12, we can collect the gas by two ways, either collected by the use of a gas syringe, and this is a very accurate method, or else we collected over water in an inverted cylinder, graduated, of course, cylinder. But of course, this method, we should take care that our gas does not dissolve in water. Okay, so
Mhm.
if we take this reaction, we are going to get a certain, of course, we get a flat bottom flask, and we get excess of hydrochloric acid because we want one of our products is hydrochloric acid. And before we place magnesium that we wanted to react with HCl, we are going to prepare our system to bring a rubber bung, or as you see here, any rubber that is connected by a tube to a gas syringe. And we should prepare our stop watch or stop clock. And as soon we are prepared, then we are going to place the rubber bung in the flask. And before placing it, we are going to add the magnesium ribbon. And then at once we place the rubber bung, and at the same time, we start our stop clock or stopwatch. Okay. Of course,
Mhm.
when magnesium reacts with HCl, it's going to form magnesium chloride and it's going to produce hydrogen gas. And this hydrogen gas is going to evolve here in the tube and goes straight right to the gas syringe. And on doing so, of course, the gas syringe at the beginning was at the zero volume, but when the gas comes out here, it's going to push the plunger of the gas syringe, and the plunger will be pushed backward so that here the gas will fill this space. And in this way, we can calculate the volume of the gas per unit time. Per unit time, it could be per 30 seconds or per 2 minutes or whatever. Okay. So here at the beginning, for example, the gas syringe was at the 0 volume, and then after the hydrogen gas entered the gas syringe, then we can measure, for example, it took about, it filled about 20 centimeter cube of the gas syringe at the end of the reaction. But we take, as we said, the volume per unit time. It means every now and then we can collect the volume of the gas produced, the hydrogen gas, every, for example, half a minute. So here, these are the results of one of the experiments where the volume of hydrogen gas collected was, of course, 0 at the beginning of the reaction. And after half a minute, then 8 centimeter cube of hydrogen gas were collected in the gas syringe. After 1 minute, it was 14, and so on, until we reach a volume of the hydrogen gas after which it will not increase. Why the volume will not increase in this area after 5 minutes? The volume of the hydrogen gas produced did not increase. Why?
Because the reaction between the magnesium and the hydrochloric acid is finished.
Yes, excellent. And why is it finished?
Because the magnesium
yes
has reacted.
Yes, excellent. All the magnesium has been used up because in the experiment, excellent, Veronica, because here we placed excess of hydrochloric acid. And this means that the magnesium ribbon is the limiting reactant. When all of it reacted with the acid, nothing is left from it, then no hydrogen gas will be produced. Okay, so here we put the magnesium. Sometimes they ask us, how can we improve of such a reaction? Because maybe as we were putting the rubber band and preparing our stop clock, maybe some of the gas disappeared, or some of the gas escaped from the reaction mixture. So sometimes we can say that we are going to place our magnesium ribbon. We are going to put it here in a wire, and then as soon as we start the reaction, then we can pull the wire so that the magnesium ribbon falls. At the beginning, it was at this position, and then when the reaction starts, then we can lower the magnesium ribbon in the hydrochloric acid. You understand what I mean?
Yeah.
At the beginning, we can use a wire and put the magnesium on this wire. Okay, and after we place the rubber band, and as we are completely ready to start our stopwatch, then we are going to lower this ribbon. We are going to lower this wire so that the magnesium ribbon will be in contact with the HCl, and the reaction will start as soon as we are ready for the reaction. Okay, now as we've seen that we've added magnesium as the limiting reactant, and HCl was in excess. So when the magnesium, all of it reacted, then no more hydrogen gas will be obtained. So if we draw the volume of hydrogen gas in centimeter cube against the time in minutes, we will find that we get this curve, that at the beginning we had 0 of hydrogen gas, and with time, the concentration or the volume of the hydrogen gas increased until we reached a point where no more hydrogen gas will be produced, which means that all the reactants now, the reactants such as magnesium, all of it reacted already. And so we measure the time at which the reaction was complete. Then we are going to measure here the volume at which, the time at which the reaction is complete. And of course, we measure the maximum volume of we obtained in this reaction. So this is the beginning of the time and the total volume. And so the rate is equal to, the rate will be equal to the volume of the hydrogen gas produced divided by the total volume, divided by the total time. It means that we can divide 40 centimeter cube by the time which is 5 minutes, and we say that the rate equals 8 centimeter cube per minute. But what we've measured here is called the average rate. This is called the average rate. This is the average rate. At the end, we took the total volume divided by the total time. We get what we call the average rate. But if I want to measure the rate, for example, between minutes 1 and 2, because as you see here that the curve is not having the same slope. You will see that the curve began steep, and then it became less steeper until it became a flat line. And this decrease in steepness means that the rate is decreasing with time. When we started at the beginning, the rate was the maximum, and then the rate decreased with time. The more the time, the rate decreases with time. Okay?
Mm-hmm. Yes.
Okay, yes, I'm just lowering the phone's volume. Okay, now this means that the rate decreases with time. So what if we want to measure the rate between minutes 1 and 2, for example? If I want to measure the rate between these 2 points, between minutes 1 and 2, then I will calculate, I'm going to say between minutes 1 and 2, between minutes 1 and 2 minutes. Then I'm going to take, for example, this volume. I'm going to say V2 over V1, and this is T2 minus T1. So I'm going to say that here I have 25, so the rate equals 25 minus 15 divided by 2 minus 1. And so I get the rate equals to 10 centimeter cube per minute. Okay, so between minutes 1 and 2, we get the rate equals V2, which is 25 minus V1, which is 15 divided by 2 minus 1. Okay, what if I take the rate between these 2 points, between minutes 2 and 3? So we will say that, so we will say here the volume was, this is 30, 32, no, 31, 32, 33. So it's the rate equals 33 minus 25 divided by 3 minus 2. This makes 13 minus 5, this makes 8 centimeter cube per minute. Okay. What about between minutes 3 and 4? It will be between 3 and 4.
38 minus 33.
38 minus 33 divided by 4 minus 3.
4 minus 3.
This makes 5 centimeter cube per minute, isn't it? So you will see here that the rate decreases with time. As time passes by, the rate at the beginning, of course, this is not the beginning, this is between minutes 1 and 2, but if you measure the rate here, it will be about 14 centimeter cube per minute from V1 to 0 minus T1 divided by T1 minus 0. This makes about 13 or maybe 14, even 1, 2, 3, 4. It's 14 centimeter cube per minute from minute 0 to minute 1. Okay, so it was 14, then decreased to 10, then decreased to 8, and then decreased to 5. And here it will be decrease more and more. So this means that the rate decreases with time. And you will see this from the steepness of the curve. You will find that the curve gets less steeper as the reaction goes by until we get a flat line. It means that the rate here is equal to 0. The rate here equals to 0. And this means that this is the total volume of the gas that we can obtain. But if we take the total volume divided by the total time, we get what we call the average rate. Okay?
Okay. Why does the reaction rate start at a higher number than decreases?
It usually do so because the reaction at the beginning, there was no product obtained. At the beginning, there were zero product. And so when it starts to form, then the rate of the reaction is the reactants have high concentration because the rate depends upon the concentration of the reactants. So the more the concentration, the higher will be the rate. And as the concentration of the reactants decreases with time, we will find that the rate will decrease as well, because there are not as many, there is no more concentration, but the concentration is decreasing with time.
Okay.
Okay. Now, you can also be asked to calculate, for example, the concentration at a certain time. For example, if he says, what is the rate at minute 3 itself, not between an interval 2 and 3, maybe he will ask you to calculate the rate at a certain time, at 3 minutes exactly. So what are we going to do in this case? If he asked us to calculate the rate at point or at minute 3 exactly, then we have to draw a tangent to this point. We have to draw a tangent to this point. Okay. You are going to draw a tangent to this point that he is asking you to calculate the rate at. And then you are going to calculate the slope of this point. You are going to choose any 2 points, any 2 points. And of course, the more distance they are from each other is better. And you calculate y2 minus y1 over x2 minus x1. You understand? We are going to calculate the slope or the gradient of this straight line by taking any 2 points on it and finding its y and x axis, y and x, y2 and here x2, and here y1 and here x1, and then you say that the slope or the gradient, the slope equals y2 minus y1 over x2 minus x1, from which you can get the rate. The slope is equal to the rate of the reaction at a certain point. At any point, you will take a tangent to this point and find its slope or its gradient, from which you can calculate the rate. Okay, Veronica?
Yes.
Okay. So we've seen that, that the rate changes all through the reaction. It is greatest at the beginning because still the reactant has a high concentration, and then at the end, it becomes zero. It decreases with time until it becomes zero. Okay, so as we see here in this graph, we will see that the curve is the steepest at the beginning, and then during the reaction, it becomes less and less steeper until it becomes a flat line. And the average rate from here is 8 centimeter cube per minute. Now, this was a reaction. This was an example at which we can study the rate of a reaction that can produce a gas. Okay, there's also another method by which we can measure the rate of the reaction if one of our products is a gas, like for example, carbon dioxide gas. So by looking at this experiment, we have calcium carbonate solid plus hydrochloric acid aqueous gives calcium chloride aqueous plus water liquid plus carbon dioxide. We will see that carbon dioxide gas here is also a gas that evolves in this reaction. Of course, we can measure the volume of this carbon dioxide gas using also a gas syringe, but this is another method, is to place the flask that we are going to do our experiment in, and we place it on a balance, and we prepare our stop clock, and then we are going to add the excess of the acid also here in the flask, and then we are going to place a certain amount or a certain mass of the calcium carbonate, which we call marble chips, and as soon as we put the marble chips or the calcium carbonate here, we are going to place a cotton wool at the top of the container, okay? And every half minute or every 1 minute, we read what is the change in the balance here. Of course, at the beginning, there was a certain mass, and then with time, this mass will decrease. Why will it decrease with time? Why will the mass decrease with time of the reaction here?
Will some of the mixture evaporate?
Yes, which part of it will evaporate? Yes, excellent.
The acid?
Okay, not the acid. You see here in this reaction, we have calcium carbonate plus HCl.
Oh, the
gives,
carbon dioxide.
yes, carbon dioxide will escape through the container. We placed here a cotton wool so as to allow the carbon dioxide to escape from the container so that the mass here will decrease, isn't it?
Mm-hmm.
In this method, we are going to study what happens to the mass of the reaction mixture with time. Or else we can measure the mass of carbon dioxide that escapes per unit time, either this or that. Okay?
Mm-hmm.
So we are going to place here a cotton wool to allow for the passage of carbon dioxide gas. But why do we put this cotton wool? Why don't we leave it without a cotton wool and the carbon dioxide will escape as well? Why did we place this cotton wool? Sometimes they ask you such a question.
To stop?
Yes.
Is it to stop the water from evaporating, or like going past it?
No, it's not because to stop the water from evaporating. No. Here we are not boiling. Here we are just placing the reaction on a balance. We are not boiling for the water to escape. Understand? We are not using heat here. We are just placing the container over a balance to study what happens to the mass of this container with time.
Is it to stop the spitting?
Yes, excellent. To stop the spitting outside these liquids from spitting outside the container, or the splashing of this liquid outside the container, to prevent it splashing outside, because we only want to measure the difference in mass when carbon dioxide escapes. We don't want to lose any other component in the mixture except carbon dioxide only. Okay, so excellent. Yes, we use a cotton wool to stop any liquid splashing outside the container. Okay, and now we are going to measure the change in mass with time. The change either in the mass of the container with time, or else when we had the mass of the container at the beginning of the experiment, and then with time we can subtract every two masses from each other to get the mass of carbon dioxide that has escaped from the container, either this or that. Okay. Of course, carbon dioxide is a heavy gas. So it means that by time we can measure we will see that there is a considerable mass that has been lost. If we were using, for example, hydrogen gas, if in our reaction we had hydrogen gas, then maybe we will not see the effect, because hydrogen gas is a light gas. Okay, so if it escapes away from the container, this means that the mass here will not be affected in a certain amount that we can observe it. But as carbon dioxide is a heavy gas, then if it escapes away from the flask, we can observe the change in the mass here. Understand?
Yes.
Okay, I mean that we prefer to do the first experiment because we had hydrogen as a product, and hydrogen is a light gas, so it's preferable to use the collection of its volume in a gas syringe. But carbon dioxide, as it's a heavy gas, then we can use this method to observe what happens to the mass of the container with time. So by time, more and more carbon dioxide escapes, and more the mass of the container will decrease until all the calcium carbonate or the marble chips have been reacted. all of it reacted, because usually we put here excess of the acid, so all of it has been reacted, and so we will find that no more gas will escape and the mass of the container will remain the same. So if we draw a plot between the mass of the container and with time, you will see that at the beginning, the mass of the container was something. For example, here it's 63, about 63. And then with time, we will see that as carbon dioxide escapes from the container, the mass of the container decreases with time until we reach a volume or a mass that will not change. This is the mass of the remaining, or the remainder of the reaction. Calcium chloride and water here will still remain in the reaction vessel. They will not escape, and so we will not get a zero mass, but this mass will be at a certain part and it will not decrease more. Okay, so for example, if we started with at time zero with the mass of the reaction mixture 63, mass of the flask, of course, with the reaction mixture was 63. And so at the beginning, no carbon dioxide was lost. With time, we will see that the mass of the flask will decrease, or else we can subtract 63 minus 62.4. We get the mass of carbon dioxide that escaped, or 62.4 minus 63 minus 62, we get 1. 63 minus 61.7, we get 1.3. This is the mass of carbon dioxide that escaped. And this is the mass of the container as a whole that is decreasing with time. So if we draw the mass of carbon dioxide with time and we get this curve, so this is the volume time graph, or the mass time graph, and from which we can calculate the average rate of the reaction, or else we can calculate the rate at any point he asks us about. Okay. Now, if we started here with the concentration of the hydrochloric acid to be 0.5 moles per decimeter cube in this reaction, we started with the concentration of the acid to be 0.5 moles per decimeter cube. So what will happen if we increase the concentration of hydrochloric acid, maybe from 0.5 to 1 mole per decimeter cube? What do you think will happen to the rate of the reaction?
Increase?
Yes, excellent. The rate will increase, and you will see this increase on the graph. You will see that as we increase the concentration of HCl, we will find that the curve becomes steeper. The curve becomes steeper. This means that the rate increased. Okay, we'll find that the rate increased. And if we increase the concentration of HCl more and more, 2 moles per decimeter cube, we will find that the rate will increase more. Of course, we can determine this increase by the steepness of the curve. The more steeper the curve, the more is the increase in the rate. Okay?
Yeah.
Okay. Now, another experiment will be done if our reaction does not include the production of a gas. So we have to find another way to measure the rate of the reaction. Okay, if one of our products is not a gas, then we have to find another way, because we are not going to get a volume of a gas. So, for example, if we take this reaction, sodium thiosulfate plus hydrochloric acid gives sodium chloride plus sulfur dioxide plus water, and sulfur solid yellow precipitate is formed. Okay, here we have sodium thiosulfate reacting with hydrochloric acid to form sodium chloride aqueous, sulfur dioxide aqueous, water liquid, and sulfur is a yellow solid that's going to be formed. So if we have such a reaction, how are we going to study the rate of such a reaction? We are going to use the fact that we get a yellow solid. When we get a yellow solid, we can do, or not only a yellow solid, but if we can get a solid in our reaction mixture, then we can use this experiment. In this
Miss,
experiment, yes.
how is it a yellow solid if it's not a transition?
It's not a
That's all.
transition. It's not a transition, yes, but it's yellow. Sulfur has a yellow color. You mean we in transition metals themselves are not colored.
They're compounds.
Yes, their compounds are the ones to be colored, not themselves. But sulfur has a yellow color.
Oh, okay.
Okay.
Mhm.
Now, here we are going to get a piece of paper and draw a cross on this piece of paper. And then we are going to place a conical flask on this cross and look from up here. At the beginning, we are going to add the hydrochloric acid, and then we are going to add the sodium thiosulfate solution. The hydrochloric acid has a certain concentration, for example, 1 mole per decimeter cube. And we are going to add sodium thiosulfate solution. And then we are going, at the same time as we added the sodium thiosulfate solution, we are going to start our stopwatch. And then we will wait, looking at, from upward here, looking at the cross, until we see that we cannot anymore see the cross. We cannot see the cross anymore. It disappeared. It disappeared, of course, because of the precipitation of this sulfur or this yellow precipitate that prevented us from seeing the cross anymore. Okay?
Yeah.
So here at the beginning, we were able to see the cross clearly. And then by time, the cross starts to fade until at a certain instant, we cannot see the cross at all. So we stop our stopwatch and measure the time from the beginning of the experiment till the point or till the time that we cannot see the cross anymore. So of course, we know that the rate is inversely proportional to time. Rate is inversely proportional to time. It means that the less time it takes for a reaction, this means that the rate is high. Whenever we have lower time, then the rate is high. Okay? So we started with a certain concentration of acid. If we want to study the effect of the concentration of the hydrochloric acid on the rate of such a reaction, then we can repeat the experiment using different concentrations of hydrochloric acid. Repeat using different concentrations of hydrochloric acid. At the beginning, we started with, for example, 0.5 mole per decimeter cube. Then we can change it to 1 moles per decimeter cube or 1.5 and so on. We change the concentration and see what happens to the rate of the reaction. Okay.
Okay.
So we will see that as the concentration of hydrochloric acid increases, we will see that the time needed for the cross to disappear will also decrease. Okay, as the concentration increases of hydrochloric acid, we will see that the time needed for the cross to disappear will also decrease. It means that as we increase the concentration of HCl, the rate increases because the time gets smaller.
Okay.
Okay, there are, of course, other methods to measure the rates of the reaction depending on the reaction itself. For example, if we are making a reaction between hydrochloric acid and sodium hydroxide, then we can measure the change in temperature per time. What happens to the temperature? Of course, when we add any acid to any base, especially if they are strong, this is an exothermic reaction. Exothermic means that its temperature will raise per unit time until it reaches a maximum, after which it will start to decrease once more. So by measuring what happens to the temperature with time, we are measuring the rate of such a reaction. Okay, or for example, measuring the change in pH of the reaction mixture per unit time. Also, this will give us the rate of the reaction. Or if one of our compounds either the reactants or the products was a colored compound, then we can measure the rate by studying what happens to the color of this compound. If its intensity becomes lower, or if it becomes higher, then we can measure the rate of such a reaction with time. Okay. As here, for example, there is a reaction that is called the iodine clock reaction, where we add two solutions together. Solution 1 contains an acidified potassium iodate and starch. We put the starch to indicate when iodine is going to be formed, iodine I2, because maybe from biology you will know that starch with iodine forms a blue-black solution, a blue-black colored solution. So we place starch with the potassium iodate here because starch will react with the iodine produced in this reaction to form the blue-black color solution. So we get two solutions. Solution 1 containing acidified potassium iodate and starch, and solution 2 we get aqueous potassium iodide, and then we start to add solution 2 on solution 1. So a reaction will take place between the potassium iodide and the potassium iodate, and iodine is going to be produced. The time that iodine is produced, it will react with starch and forms the blue color. Okay, and so when we see the blue color, we are going to stop the stopwatch and we can study how much time did it take for this reaction to take place. Okay.
Okay.
Okay, now we are going to start to study what are the factors affecting the rate of the reaction. What affects the rate of the reaction? What makes a chemical reaction go faster or go slower? So we have 5 different factors affecting the rate of any reaction. The first factor is the concentration of one of the reactants or both. And in case of gases, if our reaction is in the form of a gas, we can measure what happens to the effect of pressure. We will study the effect of temperature on the reaction rate, the effect of surface area on the reactants on the reaction rate. How does the use of a catalyst affect the reaction rate? And if we are having a photochemical reaction, it means that it's a chemical reaction that is affected by light. Then we will see what happens if the light is more intense or is less intense. What effect does this have on the rate of a reaction? So we want to study these factors, and the first factor to study is the effect of concentration. We are going to do the same first experiment that we studied before. We're going to add excess of hydrochloric acid, and we put it, or we place it in this flask, and then we are going to add a piece of magnesium metal to the acid. And as we've seen before, this will produce a salt that is soluble in the solution, and we get hydrogen gas. And this hydrogen gas, we are going to collect it and measure its volume in a gas syringe. Now, in this experiment, we are going to see what is the effect of concentration. So, of course, magnesium is a solid. It has no concentration. But as hydrochloric acid is an aqueous solution, we can prepare it in different concentrations. So, for example, if we are going to make a FAIR test means that to to compare between two experiments or more, we can set all of the variables constant except only one variable that we want to calculate. So here I want to see what will if I change the concentration of hydrochloric acid, will it change the rate of the reaction or not? So I have to make some variables constant. What are these variables? At the beginning, we should place the same mass of magnesium ribbon in the flask. For example, if I'm going to do to compare between two experiments, then I'm going to put here the same mass of magnesium ribbon. It should be placed the same mass. We should place the same volume of the acid. But of course, we are measuring the rate of the reaction, what happens to it upon the changing concentration of the acid. So I will make the volume constant. I will change the concentration only. So here, if I take 50 centimeter cube of hydrochloric acid with a certain concentration, let it be, for example, 0.1 mole per decimeter cube. And on the other vessel, we are going to use the same mass of magnesium ribbon. We are going to use the same volume of hydrochloric acid, but the difference here is in what? What is the difference here?
It's twice as concentrated.
Yes, excellent. That the concentration in this second vessel in B is more concentrated than in A. Okay, and we are going to measure the volume of the hydrogen gas produced with time in both experiments. We will find that here, when we were using, for example, 0.1 mole per decimeter cube of hydrochloric acid, for example, this is A, we will get this curve that is A, that as we see here, the volume of hydrogen gas increases until it reaches a maximum where it will not increase more because we said that the magnesium ribbon will be completely reacted, and we get this time needed for the completion of the reaction. It's, for example, 114, I think. 110, no, 12, 13, 14, yes, it's 114 seconds, okay, or minutes maybe, seconds, okay. Now, in the second experiment, where we changed the concentration of hydrochloric acid from 0.1 moles per decimeter cube to 0.2 moles per decimeter cubed, it means that we increased the concentration of hydrochloric acid to twice the value at the beginning. We will find that we get this curve B.
Mm-hmm.
As you see, of course, that curve B is steeper than curve A, and we reached the volume, the maximum volume of hydrogen gas produced after 60 seconds. So the curve was steeper. It means that the reaction rate was faster, and we got our maximum volume, the same maximum volume we got, but at a smaller time, at less time. And this means that, what do we conclude from this experiment?
The more concentrated the volume, the more concentrated the acid,
Yes.
the faster the rate of the reaction will be.
Yes, excellent. The more concentrated the acid, the faster will be the reaction. Yes, excellent. So this is our conclusion from this experiment. Okay, so this is the first thing that we concluded, that the more the concentration of the reaction, one of the reactants, like for example here HCl, the more it is concentrated, the faster will be the rate. And it was found that doubling the concentration of the acid doubles the rate of the reaction. Okay. So when does the rate only increases, and when do both the rate and the amount of product obtained increases? Okay, now here in this experiment, we used the same mass of the magnesium ribbon, and we used the same volume of hydrochloric acid, but here we used the concentration of hydrochloric acid was the one that we doubled. Okay, now, and in this way we got a steeper curve. It means that the rate was faster, but we got the same volume of hydrogen gas. Now, if we not only increase the concentration of hydrochloric acid, but we increase the mass of the magnesium ribbon from 0.05 grams, for example, to 1 gram. Instead here of 0.05 gram, we increased it to 0.1 gram. Of magnesium ribbon. What will be the difference in our result? Here we were using excess of the hydrochloric acid, isn't it? When we added 50 centimeter cube, we used excess of the hydrochloric acid. So here we not only increased the concentration of hydrochloric acid to the double, but we also increased the mass of the magnesium ribbon to be 0.1 instead of 0.05 grams. So what will happen? What do you think will happen?
The rates of reaction will be fast, but it won't last as long.
The rate of the reaction will be fast, but
it won't last as long. Oh wait, did we increase? We increased the mass.
We increased two things. We increased the concentration of hydrochloric acid, and we said that since it is present in excess, then this means that it will increase the rate of the reaction. Okay? But now we increased also the mass of the magnesium ribbon that we started with. So what do you think will happen? Will the amount of the gas be the same? Because here when we increase the concentration of the acid only and we left the mass of magnesium as it is, the rate of the reaction increased, but we got the same volume of hydrogen gas. Now, if I increase the concentration of magnesium, if I increase the mass of the magnesium, of course here the magnesium is the limiting reactant.
Yes.
The limiting reactant because HCl is present in excess. So what happens to the volume of the hydrogen gas produced? Will it be the same or will it differ?
Differ?
Yes, of course, it will differ. It will be double the volume. Why?
Yes.
Because magnesium is the limiting reactant. Limiting reactant means that when it finishes, then the reaction will stop, isn't it? So here, when it was just 0.05 gram, the reaction stopped here at this volume. But if I increased the mass to 0.1, it means that I increased to the double. We will see that the reaction rate not only increases, but also we get a volume that is double the volume at the beginning. Okay? Understand what I mean?
Yes.
Because magnesium is the limiting reactant. It means that if I place 0.05 gram of magnesium, it will give me a certain volume of hydrogen gas, which was, for example, 60 centimeter cube, isn't it? But if I increase the mass of the magnesium ribbon to 1 gram, now more magnesium is present in the reaction vessel. Magnesium reacts with hydrochloric acid to form magnesium chloride plus hydrogen gas, isn't it? So if I increase the mass of magnesium, more hydrogen will be produced, isn't it? Because it's the limiting reactant.
Yeah.
Understand, Veronica?
Yes.
Okay, so this means that if I increase the mass of the limiting reactant, then, and I also increase the concentration of hydrochloric acid, then two things will happen. The rate of the reaction increases, and the volume of hydrogen gas obtained will be more. The more I add of the magnesium ribbon, the more hydrogen gas will be obtained. Okay, so we will find that the curve becomes higher. The volume obtained will be higher than the beginning. So if the mass or concentration of the limiting reactant increases, but the same volume, then both the rate and the amount of the product will increase. If I increase the mass of the limiting reactant, then the rate will increase and the amount of the product will increase. If the mass or concentration of the limiting reactant increases, different volume, I have different volume, then calculate the number of moles first to determine, okay, yani don't bother yourself by this. But here it means that if magnesium is the limiting reactant, if the magnesium is the limiting reactant and HCl is in excess, so if we increase the volume of HCl, it will not affect the rate of the reaction. Why? Because already from the beginning, we are placing excess of HCl.
Mm-hmm.
And so if you add more and more HCl, the rate will not be affected. It's not the volume that affects the rate, it's the concentration. If I use a certain concentration of HCl, for example, 0.1 mole per decimeter cube, I used 50 centimeter cube. And we say that this 50 centimeter cube is in excess. 50 centimeter cube of HCl and excess, having concentration of 0.1 mole per decimeter cube. If I added HCl, this time another experiment, 100 centimeter cube, and with the same concentration, then nothing will happen to the rate of the reaction, because already from the beginning it was in excess. This 50 was in excess, and I added more and more of the acid, so this will not affect the rate of the reaction. Understand what I mean?
Yeah, kind of.
Kind of. This means that you do not understand, isn't it? If we add here the acid with the same concentration, but I increase the volume, it will not affect the rate of the reaction.
Because it's the concentration that
Yes, it's the concentration that affects the rate of the reaction, not the volume. And the volume from the beginning was in excess. So if you add more and more, it will not affect the yield of the reaction.
There's just more in excess.
Yes, because it was already in excess. And at the same time, we didn't change the concentration. So the rate will not increase.
Okay.
But if the magnesium is the limiting reactant and we increase the concentration of the acid, so what will happen to the rate?
It increases.
Yes, it will increase, but we will get the same volume of hydrogen gas obtained because magnesium was the limiting reactant.
Would the question tell us which one was the limiting reactant?
No.
Or do we figure it out?
Yes, you will figure it out. If he says excess HCl, this means that the other one is the limiting reactant, the other reactant.
Oh.
Isn't it?
Right, yes.
Okay. Now, if HCl was the limiting reactant itself, if HCl was the one that was present in small amount, then increasing its concentration will also lead to the increase in the rate, but we didn't increase its volume. So the rate increases. But if the same concentration of HCl was used, but we doubled the volume, this means that the volume of the gas obtained will be the double. Okay, understand?
Yeah.
And if we increase both the concentration of volume of HCl, which is the limiting reactant, then the rate will increase and also the volume of the gas obtained will be increased. Okay. So in this case here, we only increase the concentration of HCl, but here, if the volume of the gas formed here, the volume is double the one obtained in the first experiment. This means that the concentration of the limiting reactant increased to the double. That's why the volume of hydrogen gas obtained was also increased to the double. Understand what I mean, or shall I repeat this?
Yes, I understand.
Okay. Now, we come to the collision theory. What is the collision theory? Of course, we are going to study what is the effect of temperature, the effect of surface area and catalyst on the rate of the reaction. But after we take what is collision theory and what does collision theory states. Now, there's a theory that is called collision theory that stated that for any reaction to take place, for example, between reactant A and reactant B, then the first step for these two reactants to form a reaction that they must collide together first. A and B must collide together in order for a reaction to take place. But if A and B did not collide, A was moving in this direction and B was moving in that direction, they did not meet, they did not collide, then no reaction will take place from the beginning. So for any reaction to take place, the reactants A and B must collide together. Okay, but this theory states that not every collision, not every collision is a successful collision. Not every collision is a successful collision. What do we mean by successful collision? Do you know? It means that not every collision will result in the formation of a product. Successful collision means that it will result in the formation of a product. So not every two particles colliding together will lead to a reaction, but they must collide together with, they must collide together with an energy enough and we call this energy, we call it the activation energy. They must collide together with energy enough to form the product. They must collide together with a big energy that is called the activation energy for this reaction to take place. So this theory, the collision theory, stated that for any two particles to form a reaction, they must collide together first. But not every collision is a successful collision. Not every collision will result in the formation of a product. The products will be formed only if A and B collided together with a certain amount of energy that is called the activation energy in order to form the products. Okay?
Okay, yeah.
Okay, now we come to the second effect on on the rate of the reaction, which is the effect of temperature. Now, according to the collision theory now, we stated that in order for a reaction to take place, then the two particles that will collide together must have enough energy to form the reaction. Okay, so now if we take into account our second experiment, that was sodium thiosulfate reacting with hydrochloric acid to form sodium chloride, sulfur dioxide, water, and the yellow precipitate, at which we placed a cross below a conical flask, and we added the two solutions together, and we calculated the time until the cross has disappeared. You remember this experiment? You remember this experiment, Veronica? You don't?
Kind of.
When we put the piece of paper and we put the cross and we placed a conical flask over this cross, and we were looking from here, from upward here, isn't it? And we said that,
the yellow precipitate.
Yes, we said, yes, this is the yellow precipitate that is going to be formed. And we said that we will measure the time from the addition of the sodium thiosulfate on the HCl till the cross disappears, or we cannot see it, isn't it? And we said that if we increase the concentration of hydrochloric acid, we have seen that the rate of the decrease of this cross was faster. The more we increase the concentration of hydrochloric acid, the faster is the rate in the disappearance of this yellow precipitate. Okay, So now we are going to repeat this experiment, but this time we are going to leave the concentration of HCl the same, but we are going to change the temperature at which we are doing this reaction. So we get the same concentration of HCl, but we are going to, in an experiment, we are going to measure the rate at room temperature of the disappearance of the cross by the formation of this yellow solid. Okay, we measure the time needed for the disappearance of the cross at room temperature. And then we are going to repeat the experiment using the same concentrations of HCl, the same volume of HCl. We are going here to use same concentration of HCl. We use the same volume of HCl. And of course, we are going to use the same concentration and volume of the sodium thiosulfate solution. So what will be the difference only? The difference will be in the temperature used. This will be the only difference, is the temperature used in every experiment. Okay.
Isn't it dangerous to put our eye above the flask while it's heating?
Yes, of course. Yes, of course. But we will not do this while it is heated. We are going to heat the HCl first until it reaches this temperature, and then we are going to add the sodium thiosulfate.
Okay, I was kind of confused.
Yes, of course. Of course, if you are looking from upward and you are heating something, then it can splash into your eyes. Yes, really, it's very dangerous. Yes, of course. But what we are going to do here is to warm the HCl or to raise its temperature. And then we are going to add the sodium thiosulfate and see what happens. Okay, Veronica? Yes. Of course, we care about your eyes and we care about your health. Yes, yes, of course. So now when the temperature of the HCl reaches 30, we are going to take it away from the heater, and then we are going to place sodium thiosulfate and measure the time needed for the cross to disappear. So for example, if at the first experiment when we were using room temperature, the time needed for the cross to disappear was 200 seconds, and at 30 degrees Celsius, we found it to be 125 seconds. If we heat in a third experiment HCl to 40 degrees Celsius and then measure the time needed for the cross to disappear, it was 50, and so on, we will find that the more the temperature, the less time it will take for the cross to disappear. And this means that the rate increases. The rate of the disappearance of the cross will be increased. Okay. We will see that as the temperature increases by 10 degrees Celsius, the rate generally doubles. But of course, if you are going to study chemistry as an AS, you will find that this statement is not true. This statement is not true. But they say it in O level, yani, but it's not true. Okay.
It's not true?
Yes, not always. It is true, not always. It's not always true. Okay. So if we draw the temperature of the sodium thiosulfate or the temperature of the reaction mixture against time, we will find that as the temperature increased, then the time needed for the cross to disappear is small. This means that the rate is faster. But as the temperature decreases, then we will find that it will take more time for the cross to disappear, and this means that the rate becomes slower. Okay.
Yeah, okay.
So the higher the temperature, the shorter is the time taken, or the lower is the time taken for the yellow sulfur precipitate to appear, and the faster the X sign to disappear. Now we come to the third factor, which is the surface area. Surface area means the particle size. So we are going to use this experiment at which we measured a certain amount of a certain volume of the acid, place them in a flask, a flat bottom flask on a balance, and we added marble chips. Marble chips of calcium carbonate, it means big lumps of marble chips. Here we have big lumps. We call these big lumps. Big lumps of marble chips. It means large pieces of calcium carbonate. We are going to use these lumps of marble chips once, and then we are going to repeat the experiment, but using E by crushing and using small pieces.
The small pieces are better.
Yes, of course. The small pieces means that we will find that, as you said, the reaction rate will be faster on using small pieces. Why is it faster? Why is it faster in case of using the small pieces?
Because it has a larger surface area.
Yes, excellent, because it has a larger surface area, and of course we are going to see. Now, what happens
It's also
if I...
smaller, so
Yes, it's smaller, and this
faster.
means that, yes, why is it faster? Let us imagine that we are having here only one piece of sodium, of calcium carbonate. This is one piece of calcium carbonate, and it reacts with HCl. So when HCl wants to react with this calcium carbonate, it will see that it will have only to react with the outside surface of the calcium carbonate lump. It will not be able to enter inside the calcium carbonate to react with. So the only area or the only surface that it has to react on is only the outer surface only. Okay, so this is a lump of this. So what happens if I did what? I crushed this lump of calcium carbonate into 4 pieces. So I got this piece, I got another piece, I got here a third piece, and the fourth piece. So where will the acid react now? Here are the original places where the acid could react. These outer spaces only.
And the inside.
Not even this. It's only here, the outside only. Okay? These were the places at the beginning where it can react with the calcium carbonate. But now when we divided this lump into 4 pieces, the hydrochloric acid can react from other places as well. It can react from here or there. It can react from here or there, isn't it? Can react now from more places.
Yeah.
So what do you think about the rate of the reaction? Will it increase or decrease?
Increase.
Yes, excellent. It will increase because as we increased the surface area of the solid, then the HCl reacted more. It has seen more spaces or more places to react with the calcium carbonate. And as it did so, the rate of the reaction increased. So here we were using here, this is the lump of calcium carbonate, and here the pink one are the HCl reacting with it. And we will see that after 30 seconds, only the molecules that are at the surface of the calcium carbonate are the ones to react with the pink ones and forms the product. But the inner molecules did not collide with the other reactant. So collision here takes place between HCl and the surface of the calcium carbonate lumps only. And the product formed will be corresponding to this amount of calcium carbonate at the surface. But if we divided this lump into 4 parts, then this means that the acid will will react more with the, I mean, from more places with the calcium carbonate, and so more product will be obtained at the same time that was used in the beginning of the experiment, at the first experiment. You understand?
Mhm.
So increasing the surface area will increase the collision. Why does the rate increase? Because it will increase the number of frequent collisions. We say so. We always use this expression. We say that increasing the concentration or increasing the surface area, increasing the surface area increases the number of frequent collision, increases the number of frequent collisions between the two reactants. So increasing the rate. So the rate becomes faster. Okay. Understand, Veronica?
Yes.
Okay. So as you see here, if this is the total amount of product made and this is the time of the reaction, we find that in the first one, where we had smaller surface area, we were using lumps of calcium carbonate, we got this curve. But when we crushed the lumps and formed small pieces or even powder, the more they are in the powder form, we will find that the rate increases, and we observe this from the steepness of the curve, and it will take less time to form the total amount of product that should be formed. Okay.
Mhm.
Of course, although increasing more and more surface area, this will increase the rate of the reaction, but sometimes this is not a good thing. Sometimes it's harmful because, for example, as we can see in flour mills, as the flour become more and more in the powder form, we will see that sometimes explosion takes place at flour mills because the reaction will be very vigorous between the flour and whatever is with it. In flour mills, there is a lot of flour dust in the air, and any spark from the machine could be enough to cause an explosion because the flour is very, very, very tiny particles. Okay, and this also happens in coal mines, as methane gas is flammable, so it is present in the air. So any spark would produce an explosion in the mine. Okay.
Yes.
Now we want to study the effect of using a catalyst. What is a catalyst? Do you know what's a catalyst?
It's something that speeds up chemical reactions, but it doesn't change itself.
Yes, without itself being chemically changed. Yes, excellent. So for example, if we take a reaction like this one, hydrogen peroxide by time decomposes to form water and oxygen. But if I get some hydrogen peroxide in a conical and I wait for this oxygen to be produced, I'm going to test whether oxygen is produced or not. So I'm going to approach a glowing splint to the reaction vessel. I will find that this glowing splint will not be relit. It will not relight. Why? Because this reaction is so slow. It will take a long time for oxygen to be produced. Okay, that's why the glowing splint did not light up, because oxygen is not produced yet. It's a very slow reaction. But if we added a catalyst like manganese 4 oxide to a second beaker containing hydrogen peroxide as well, and I approach a glowing splint, I will find that this glowing splint will relight in a very small time. And this means that manganese 4 oxide increased the rate of this reaction. It was a catalyst that increased the rate of the decomposition of hydrogen peroxide to water and oxygen gas, and itself did not change. So we will see that hydrogen peroxide is present here alone, but here in presence of manganese 4 oxide, we will find that the reaction is faster and faster. So the presence of a catalyst increases the rate of the reaction without itself being used. So if this was the uncatalyzed reaction, means the reaction that takes place with a small, either without any catalyst or with a small amount of catalyst. And here is the reaction on using the big amount of catalyst. So the reaction gets steeper, the curve gets steeper, means that the rate is faster, and we get the same volume of oxygen gas that should have been obtained if we decompose hydrogen peroxide alone without any catalyst.
Okay.
Okay. Of course, as you know, that enzymes would do the same thing as catalysts, but we call them biological catalysts as enzymes increases the rate of the reactions that happens inside the body by providing active sites for reactants to come and react with, and of course to form the product.
Okay.
Okay, Veronica, do you have any question up till here?